Hello everybody, welcome back. My name is Danielle Weigel and today we are going to be finishing up problem B2 of exam 3 for the class Transport 2. In the previous video we discussed how to determine the differential equations that I have rewritten on the OneNote tab right above me for easy access. We determined how to get those, and now we are going to be using them in a problem with specific variables in order to determine the mole fraction, the temperature of the liquid, and the temperature of the gas along the position of the cooling tower. And the way we're going to do that is to be solving it with Python via Google Colaboratory. The first thing that we're going to have to do is import any of the tools that we will need in order to solve this problem. The first thing that we always have to import is NumPy, and NumPy will help us with the functionality of our arrays and matrices. We also need to import a couple tools from the SciPy library. We have to use an initial value problem solver from the scipy.integrate, and then we also will need to use a root solver, and that is in SciPy optimize. After that, we are going to be graphing our results, so we have to import some functionalities for that. And that is in the Plotly library. And then we also need, if we want our graphs to look nice and pretty, we can import this tool, plotly.io, and use it to create a dark background from their default templates. And if we shift enter, that should all work out, and it does. I already input all of the variables that were given to us in the topic above. We have the height of 20 meters. We have our heat transfer coefficient of 10 watts per meter squared Kelvin. We have our specific area for our packing, and that is 5 meters squared per meter cubed. And then we also have our temperature for the liquid at 70 degrees Celsius, and we have our temperature of the gas at 25 degrees Celsius. We are also given the liquid flow rate at half a kilogram per meter squared seconds. And then we also have the velocity of the air which is at 5 meters per second, and we also have the relative humidity at 50%. I also included some other variables that will be helpful to us later. The first thing that I'm going to want to do is make an array of values that we will be using later to plot and solve for multiple values that we're trying to solve for. What we're going to want to do is have a set of equally spaced numbers so that we can graph them. And so the first thing that we're going to do is make this zplot using the numpy linspace command. And our initial value will be 0, and our final value will be our height. And let's just go for 25 numbers. We also want to change these temperatures into Kelvin, since our other variables are in terms of Kelvin. I was making new variables for this, so we will just do it this way. Is equal to the temperature of the liquid in the feed. Let's just adjust these really quick. So that's going to be equal to the feed in Celsius plus 273.15. And the same for the temperature of the gas in the feed. It will be equal to the Celsius value plus 273.15. So then we have the flow rate of liquid, the velocity of the air, as well as the relative humidity. We can go ahead and shift enter these to lock them in. And for those other useful values, I included the density of air as 1.2 kilograms per meter cubed, as well as the specific heat of the air as 1,000 joules per kilogram Kelvin, as well as the specific heat capacity of the liquid water and the gas water at 2,000 and 4,190 joules per mole Kelvin, respectively. We also have our gas constant in terms of joule per mole Kelvin and the heat of vaporization at 40,900 joules per mole. We also have the molecular weights of the water and the air, respectively, at 18 times 10 to the negative third and 29 times 10 to the negative third kilograms per mole. And then we also have the pressure of our system, which is at 1 atmosphere, or 101,325 pascals. Since this is a moist air system, we can actually calculate our own mass transfer coefficient using the Lewis relation. So we will have the mass transfer coefficient is equal to the heat transfer coefficient divided by the density of air times the heat capacity of air, I believe. And then we also want the mole fraction of water in the air feed, and we know that that can be determined by the partial pressure of the water divided by the total pressure. If you recall, in part A2, we defined the relative humidity as the partial pressure of water in the system divided by the saturated partial pressure of the water at the given temperature. I also mentioned that the saturation partial pressure can be calculated using the Antoine equation. And so after determining the saturation pressure with the Antoine equation, we can then substitute the relative humidity and the saturation partial pressure of the water to instead of the actual partial pressure of the water. And so before this, I already looked up the Antoine equation and the parameters for it of the A, B, and C values. So go away. And then so I already looked up those values, so what we're going to have to do is define a function to determine our saturated pressure. So we will do that. We'll insert a code right here. We'll just define it as Psat for the saturation pressure, and it will be in terms of temperature. And so I have those values up there. We're just going to type them in as A is equal to 8.07131, B is equal to 1,730.63, and then C is equal to 233.426. And then we can, what we're going to return is our saturation pressure, and so that is equal to 10 to the power of A minus B divided by C plus T. And this is in parentheses. But we have to keep in mind that the Antoine equation uses different units than what we are using. So first we're going to have to take our temperature from Kelvin to Celsius. So just like we did before, we're going to be subtracting now 273.15. And then we are also need to transfer this outcome, which I think I'm missing a parenthesis. This will give us the answer in millimeters of mercury, and what we need is pascals, like we already have our pressure in down here. So in order to take this from millimeters of mercury to atmospheres, we're going to divide by 760. And then in order to take it from atmospheres to pascals, we're just going to multiply by 101,325. And that works out, so that should work. Now that we have this function defined, we can go ahead and write a function for our mole fraction of the H2O of the water. So we're just going to call this YH2O feed, and that will be the relative humidity times the saturated pressure. So we're going to call that function, and we are going to use the temperature of the gas in the feed, and then we need to divide by the total pressure, or our atmospheric pressure, which is 1 atmosphere, or 101,325 pascals. Next, we want to have that calculate the actual flow rate of the air going in, since we only have the velocity currently. So using the ideal gas law, we can go ahead and define that gas flow rate as or the air flow rate as the total pressure. We'll just call this G air, and that is defined as the total pressure times the molecular weight of the air, and that is divided by the product of the gas constant times the temperature of the gas in the feed. And then all of that needs to be multiplied by the velocity of the air. I think my keyboard died. Okay. Sorry. Alrighty. So, and now we need to multiply that whole thing by the velocity. Yeah, that should work. I mentioned earlier that we will be using a root function to solve for our actual values, so we need to make some estimates for the final values now. For our mole fraction of the water, we will just call this Y out G for the guess, and we aren't expecting this to change really too much along the distance of the column, but it will still change. So what we're going to use is the initial mole fraction that we defined as YH2O feed, and then we're just going to multiply it by 1.1, and that will be our initial guess there. And then we also want our guess for the temperature of the gas going out, and we'll just call this one TG out G for guess. And then that one also won't change very much either, so we'll just go with the initial temperature of the gas feed and add 5 Kelvin to it. Now we're going to define a function to hold all of our differential equations. We will define it as, oops, something is not defined. Oh, faux, it is rho. Why would you betray me like this? Okay. Lovely. CPA. Yes, that should be CA. PA is not defined. It's because it should be P. There we go. That should be correct now. Yes. So now we're going to define a function that will allow us to hold all of our differential equations. We will just call it dy tgtl for our 3 differential equations, and it will be in terms of with inputs of the position as well as some arbitrary variable v, which will be the list of the 3 values that we're going to define later. Colon. And so for that list v, our first value will be the mole fraction, so we can define that right here as this. Why would you change that? So rude. And then the temperature of the liquid is going to be in that second slot, and then the temperature of the gas is going to be in that third slot. And so then before we define our differential equations in this equation, we actually need to combine the gas flow rate of the air and the water vapor so that we can get the total gas flow rate. And the way we will do this is by comparing the ratio of the molar flow rates and the mole fraction to its components. We want the mole fraction of the water to be divided by the mole fraction of the air. So we will type this out. Our flow rate of the water is equal to the mole fraction of the air divided by, or the mole fraction of the water divided by the mole fraction of the air, which is just 1 minus that. And then add some parentheses. Then we need to multiply that times the gas flow rate of the air, and then multiply that times the ratio of our mole fraction or our molecular weight of our water to the molecular weight of our air. And then we also need to define the total gas flow rate, which is just going to be equal to the flow rate of the water plus the water vapor plus the flow rate of the air that we were kind of given and solved for earlier. Now we need to determine the average molecular weight for this gaseous system based on the flow rates. So we will divide the total gas flow rate by the sum of the ratios of the gas flow rates of air divided by the molecular weights of air, and we'll add some parentheses to make sure it all works. Plus the gas flow rate of the water divided by the molecular weight of the water. Okay, that should cover all of the parentheses. And then we need to determine the heat capacity for the entire gas system. rather than just specifically the air in the liquid in the vapor water. So we'll just define that as Cg, and we can determine that by kind of averaging out the other heat capacities in accordance with the flow rates of the gases. So we have that will be equal to the heat capacity of the air times the gas flow rate of the air plus the gas water times the flow rate of the water vapor, gas water vapor, and then divide that by the total gaseous flow rate. And now that we have that defined, we are also going to define our molar flux of our water vapor. And that is something that we defined earlier as the mass transfer coefficient divided by the product of the gas constant times the temperature of the feed water, and then that will be multiplied by the saturated pressure at our feed temperature, and that should be fine. And then we need to subtract the product of the mole fraction times the pressure, total pressure. Yes, all the parentheses are closed. So now that we have those, we can actually begin writing our differential equations. As I mentioned before, I have them written up there for ease of access. We have the differential equation for our mole fraction, and that is equal to negative specific area times the times the average molecular weight divided by the total gas flow rate, and then that is multiplied by the molar flux of the water. And then we have our differential equation for the temperature of the liquid water, and that is the specific area divided by the liquid flow rate times the heat capacity of our liquid water, and then that is multiplied by the heat transfer coefficient times the difference between the two temperatures minus the heat of vaporization times the molar flux. And then we have our third differential equation, which is for the temperature of the gas, and that is equal to frickin' gnats, the specific area times the heat transfer coefficient divided by the gas flow rate times the heat capacity, the specific heat for the liquid water, and then, or no, sorry, I was reading the wrong equation. For the gaseous water, the water vapor, and that is times the difference in the temperatures once again. And we will need to fix these. Those should be right. And what we are going to want this equation to return, let me just double check these real quick. Yeah, I think those are right. And so what we want this equation, this function to return is our three differential equations. So dy, dtl, and dtg. No immediate errors. And so next we want to nest this function within another function to allow our values to converge to the correct values. We can just call this, first of all, we'll tab these over. And then define this new function. We will just call it converge feed air at some temperature. And then our input is just going to be another arbitrary variable. And that we can define that variable as the mole fraction at the exit and the temperature of the gas at the exit. So we'll just call this one y out g, like we said, and that will be equal to the first slot in this second variable. That equal sign does not need to be there. And then the temperature of our gas out of our yes, which will be equal to the second slot. Now we will be creating a variable called sol, S-O-L, which is where we will end up solving our solve.solveIBP function. In order to make sure that this works all the way throughout the code, we're going to go all the way back up here and define sol as none. That will make sure that it doesn't have any type. And then in here we are going to, so that we can edit sol outside of its local area, we are going to have to make it a global variable. And then, actually, that's out of order. Here we go. And now that we've set that as a global variable instead of a local variable, we can go ahead and define this. It's supposed to be back. And then, so we can define sol as our solve IBP function. We want to use the dytgtl function that we defined earlier within this one. We want our t-span to be from 0 to the height. And then we want our inputs to be our initial guesses and the temperature of the feed for the liquid and our other guess there. Then we are going to set our method to rado, need an equal sign, and then we are going to solve along the whole spectrum, so we need to set our dense output to true. Equal sign, not plus. I think this has to be capitalized. And then in order to actually solve along our z plot values that we came up with earlier, we can add dot sol z plot. And Yeah, so what we want to return from this function is the values that we want to converge that we can then input into our root function later. But so what we are going to return is the first item in our system, but we want it to be the last part of that array. So all the way at z equal to 20. Yeah. But we can just put -1. That'll give us the last number in that array. And then since we want this to be equal to 0 because we're using it for our root function, we can subtract the initial mole fraction. There we go. And then we also want to return our third item as our the other guess that we inputted as where is it? The temperature of the gas. So we will once again use this -1 to choose that at z is equal to 20. And then we will be subtracting our temperature of the feed. And so that should give us negative numbers, or not negative, 0, a product of close to 0. So we can go ahead and quickly test how this is running. By inputting our initial guesses as our inputs. And then let's see what we get. Okay, errors. TH, that is why it is not defined. Oh, there it is. It says TG. There we go, let's try it again. TL, aha, yes, that would be undefined considering it is wrong. Let's try that again. Why H2 feed? That's because it's supposed to be H2O feed. This should be lowercase. And then we get these numbers, and that they're not converging to 0, so which is what we expected because they should be wrong. Yeah, so now we're going to use our root function. I'm not sure if these numbers are what they're supposed to be, but I guess we'll find out when we do the root function. So now we can go ahead and set up our actual root function. We're going to use our converge feed equation with our guesses. And when we run that, it says that the actual values for the mole fraction should be 0.05, and the gas outlet temperature should be about 302 Kelvin. So now that we have these root functions set up, we can go ahead and that allows us to solve for the actual values. We can go ahead and plot them. So the first thing we're going to do is define our figure using the make subplots command. We want 3 different rows because we're making 3 different plots. And we only need 1 column. And now that we have that figure actually made, we can go ahead and add our data to it. So we are going to use fig add scatter And then we want our x values to be on the z plot, and then we want our y-axis to have our mole fraction numbers, and we want to go all the way from 0 to the end, so we can just add a colon there to reach the end. And then we want to name that plot mole fraction of H2O. And then that should be this, so that it is a string and not a number. And then we want this in row 1 and column 1. That closes that up, and then we are going to copy this down and adjust it for each of the other two. In the first section of our array, we have the temperature of the liquid, so we want that in the second row. And then in the third slot, or the second slot of our third slot, second number of the sol function, we have the temperature of the gas stored. And so we want that in the third column. So now we can go ahead and test this. Invalid syntax. Oh, I'm missing a comma. That'll do it. And there we go. These look a little messy, so we're going to, they also don't look completely correct, so I might have to go back through and see where I messed up. But we can go ahead and update the figure with fig update layout. And then we want the width to be equal to 600 and the height equal to 900. Yes, so there is something wrong. I need to double check my values. Okay, so I think I know what the issue is. I was attributing these to their feed and the specific air values when that is not correct. Let's go ahead and pull those out of there, because they should be these values up here, not the feed values. Let's go ahead and try running that. That looks more accurate. There we go. So those are the correct values. We can see that the mole fraction of the water starts up here at about 0.025 and finishes down here at well, close to 0. And for the temperature of the liquid, we start at about 343 Kelvin and then go all the way down here to 298.5. And for the temperature of the gas, we start all the way up here at 299 Kelvin, almost 300 Kelvin, and then reduce down to 298 Kelvin. So you can see that the change is actually very small, only a couple degrees, and but it's still there. And so that is how you calculate the temperature across the system and the mole fraction across the system. If you have any questions, feel free to leave them in the comments below, and have a great night.